Hello again, we're going to be looking at a new meter. And it looks like there's a problem here. You notice that the inside insulator is basically touching the walls. This is what you would expect. See how these are made? Yeah, you can see the board doesn't quite fit flat. So it's kind of tilted up on an angle. I don't know if you'll be able to tell this, but the connector on the right is definitely slanted. That's part of the reason this thing is butting up against the edge. But the rest of the board, solder-wise, looks pretty good. One of the things I've done is I've heated up the solder joint here. Hopefully that'll solve the problem where these two are cocked up against the edge. The other thing I've done is started to trace out some of the front end of this. This is essentially the one circuit board in this area. And then this is your main board. Up on top of that small mezzanine board you have R7 and 8. These are both 1K resistors. Each one of these resistors is in series with a PTC. R7's in series with PTC1, which is a 1.5K. Now the package on that part is very small. Look at the difference in the package size of these two PTCs. I can't tell if this is like a 4mm or a 5mm disc. The thing I don't like about these small PTCs is I've had these arc over before. Of course this is going to protect it from taking the casing off, but if it arcs over, it could damage components farther down the chain. So these two PTCs then route to these MOVs. These are 07D821. That part number should sound familiar. And then those two tied together to another MOV, which is a 10D102K. And then that goes back to the common point. So if we kind of follow our inputs, you can see it comes down here. This is one of the PTCs. And then this routes up to the one connector. And the other PTC routes up to this other connector. And they're attaching to the two inside pins. And then the outside pins are not used. Those two connectors attach at these locations. And you can see I've just installed a couple of test points into those for now. So if we trace this further down, we'll see that this PTC1, which is the smaller package, goes through this 10 meg resistor. That's this one here. You can see it's a fairly large high voltage part. The other side of this resistor goes straight into the IC chip. So what I think would happen is if this PTC were to arc over, at least that pin would be protected by this resistor. However, we can see that that pin also routes up to another node that goes into our rotary switch. And that's this node here, and we can follow that down and it goes to the selector switch while it's in diode mode, resistance mode, and milliamp mode. That routes into Q11 and 12. That's this set of transistors here, so that's one of the high-speed clamps. So the other leg of that just goes to the ground. You can kind of see the star ground at this location here. That routes up through this ferrite bead. At this location, this is L3. And then back to the main ground feed, which is this wire here. I assume that L2 may be for the signal ground. If we follow the other side of the diode clamp, we'll see it goes to R24, which is a 33K. And then there's a C48, which is a no pop, and then that goes to pin 35 of U1. So if they were to have a transient, at least these transistors here would clamp, and then this resistor limits the current back into the chip. A lot of the meters I look at will only have a PTC. They won't have this added resistor. At least if this were to arc over, this will limit some of the current that's feeding down into this clamp. The other leg, PTC2, also feeds into the selector switch and this will feed into Q8 and Q9, which is another clamp. So I'm pretty confident that the meter will survive some of the basic transients. One thing that has me a little concerned about the meter is we can see there's pads for a Q4 and Q5, Q6 and Q7, and these are all no pops, and those are definitely high-speed clamps. The thing is if you look, the emitter on those two clamps is not attached. So while these are a no pop, they weren't used. However, we can see here there's an RV7, here's a RV6, and here's RV5. And these are all placeholder for what I believe are MOVs. And there's definitely traces attached to these. I'm not sure if they didn't hedge their bets, where if they were having trouble that they would add those MOVs. Those have got to be in there for the robustness of the meter. I can't believe that those would have anything to do with safety. But again, I say that about these high-speed clamps and such. Those are really there to protect the downstream components. So I've got some confidence now in the meter. I think it should do fairly well. We'll go ahead and I'll reassemble this and we'll run some tests on it. Assume this resistor down here is their current shunt for the low range. Yeah, I can tell you I'm not a big fan of this wire that they've got in here, or how they've attached this wire up in here. I can understand they're going after density. Alright, this time we're going to try to get this thing a little more squared up. Looks pretty good. That's much nicer. See how nice and even these are now? Much better. It's kind of interesting. I'm using SEBA fuses for the one. You can see it's a Bussmann in the other. Look at this. I think that's been cut away at the factory. There's no loose plastic inside of the case when I took this thing apart. I think they have an interference problem maybe there. That would basically just slide into this area here and... oh, okay. I didn't see what happened here. So they've got these little surface mount ferrites sitting there. And I'll bet you they had problems with those. And they've cut this off to give it a little clearance down in there for that. I was going to say, I didn't see anything broken inside of the case when I took this apart. There's our manufacturer number, made in Taiwan. There's our CE marking. Of course, it's UL listed. Again, 600 volt Cat 3, so shouldn't have any problems with our testing. We're going to start our testing by comparing the BM235 against the BM869S. First thing we'll do is look at resistance values. This is looking at a 1/2 ohm resistor. This is a 50 ohm resistor. This is a 1K resistor. This is with a 10K resistor. This is with a 100K resistor. And this is a 1 meg resistor. Let's see how long it takes this meter to settle down. This will be a 10 meg resistor. Now, of course, the little Brymen can't read 100 meg. Let's just try diode mode. This will be a short. And here is a single diode, 2 diodes, 3 diodes. No problem with that. Let's try it in capacitance mode. This will be a 150 picofarads. Fairly close. Takes it a long time to take the reading. This will be 1 nanofarad. This is with a 0.1 microfarad. This is a 1 microfarad, and this is with a 10 microfarad capacitor. Currently all 6 meters are attached in parallel and they're connected to my fluke calibrator. We're going to be using these 5 meters to compare against the BM235. All these meters are true RMS. On the left we have the Hioki. This is the model DT4252. It's 6,000 count. To the right of that we have the Unity UT61E. This is a 20,000 count meter. Of course, this meter's been modified if you follow my videos. This meter costs about $50 US. To the right of that we have the Fluke 115. This is also a 6,000 count meter, and the cost on this is about $132. To the far right we have 5KY's Amprobe AM530. This is a 4,000 count meter. The price on the Amprobe is about $80. Like the Brymen, this has temperature input as well. The Amprobe is also the only other one with non-contact voltage detection. One of the nice things with this meter is you can see it has a microamp range. The Hioki and the Fluke 115 do not. Both of these meters survive some very large transients. This Amprobe, on the other hand, failed at about 2 kV. Of course, this thing, yeah, what do you need to say? You look at it funny and it fails. Of course, it doesn't anymore. It also will survive a 6,000 volt hit off of that new transient generator. All the meters are reading roughly the same value. So this is currently with 1 volt applied. This is with 1 millivolt applied. Of course, the Amprobe doesn't have a millivolt range like the Fluke or the Hioki, but we can see it's able to resolve down to 100 microvolts. And we can see the Unity and the Brymen both reading 10 microvolt res. And of course, the BM869 will read down to 1 microvolt res. Again, all 6 meters are in parallel. And you can see on the Brymen I'm supplying a 100 Hz sine wave, and this is roughly 100 millivolts. And you can see I've increased the amplitude to 1 volt. What I'm going to do now is look at the 3 dB point for this meter. So what I'll do is I'll increase the frequency until this rolls off to roughly 0.71. So you can see we're at roughly 1.5 kilohertz right now. And again, 1 volt. And we can see the little Brymen's already attenuated to 0.96. Of course, the Amprobe is also 0.96. So this is at 2 kilohertz. And we can see again the Amprobe and this Brymen are roughly tracking. And this is roughly 3 kilohertz. And we can see we're almost at the 3 dB point. But let's watch how fast this rolls off here. That's 3.1 kilohertz. 3.2, 3.4. Now again, the Hioki isn't doing a whole lot better. We can see it's all the way down to 0.455. I remember when I looked at the Hioki initially, I actually wondered if there wasn't some software filter that was enabled. But it's not. It's really that bad. It's at 5 kilohertz. And we can see now the Brymen is 0.19. Basically the Hioki is nothing. Of course, the high-end Brymen staying reasonably flat. So you can see I've gone back to 100 Hertz. What I'm going to do now is switch this from a sine wave to a square. This is with a triangle wave applied. On the Brymen, we can see this is our DC content versus our AC up in the upper right. So we can see again it's roughly 1 volt AC and no offset. What I'm going to do is add a DC bias to it, and we'll see if that has any effect. You can see we're still applying a 1 volt AC signal with a 1 volt DC offset. Of course, the little Brymen isn't having any problems with this. Again, I've ran into this problem with some of the real low-end meters, but these ones that have survived all of my testing really are pretty decent meters. And now you can see I'm applying a negative 1 volt bias. And again, you can see it's not having any effect on these meters. All 6 meters are now connected to the high voltage power supply. You can see we're outputting roughly 10 volts. And this is roughly 284 volts. Here we're at roughly 500 volts. And this is roughly the upper limit of the Fluke 115. You can see as I continue to increase the voltage, it's just going to go to over range. And this is roughly the upper limit of my power supply. You can see we're reading roughly 982 volts on all the meters. And we can see the amp probe is reading just a few volts high. Again, for $80, this is actually not a bad meter. It's just too bad it doesn't handle these transient tests so well. And this is what this meter looks like on the inside. You can see this is a CBA and a large busman fuse. Very nice planes. I don't like the split connectors on it, but fairly large PTC here. You can see the 3 MOVs. Again, it's a shame that this meter doesn't do better in the testing. So you can see I'm applying roughly a 542 volt. This is a square wave and it's got an offset of roughly 3.6 volts. What I'll do is go ahead and change the bias. One thing you can notice again is this unit T actually peaks up pretty bad. Frequency on this right now is roughly 30 Hertz. You can see I've given it roughly a negative 114 volt bias, and it has no effect on the little Brymen. And this is going up the other way. This is with a positive 120 volt bias, and again no effect on the little Brymen. Next I'll give you an idea how loud this meter is. Let's just compare that with the BM869S. Of course, that Hioki has that nice red LED. So this is definitely the quietest of them. I could definitely see out in a noisy lab environment or out on a shop floor. I'd be glad that I had this backlight lighting up, because I don't think I could hear that necessarily. I think for home use though it's going to be just fine. Of course you can see our UT61's got this adaptive backlight on there, and my office right now is pretty dark. Let's have a look at the non-contact voltage. So I've just got a line cord strung across, held up with a couple of blocks of wood. The only meter I have that supports this feature is the amp probe BM530. And you see I've got to basically be right on top of that wire for it to pick this thing up. Now this is in the low sensitivity mode. What's interesting about this is we changed the mode to high. This is close to 2 feet away right now, and I'm just going to turn on the power. That's pretty impressive. So yeah, this is by far the most sensitive one that I've ever seen. So you can see I brought out the UT181A. So currently all 4 meters are tied together in series, and I've got it attached to a bench power supply, and I'll go ahead and we'll increase the current on that. So this is roughly a half an amp and roughly 2 amps and roughly 4 amps. And this is the top end of my power supply, so roughly 6.7 amps. And here we can see I've changed the leads over to the milliamp range. It's one of the things I like about this Unity. It's pretty fancy. You can see we're in the amps range. We'll go ahead and change that over to the milliamp range. Okay, I'm currently putting out about 180 milliamps. Here we're on the high side of the 20 milliamps, or roughly 24 milliamps. And here we're putting out roughly 1 milliamp. This is with all 4 meters in the microamp range. You can see all reading roughly 104 microamps. It's with roughly 10 microamps applied. Again, looks real good. And this is with roughly 800 nanoamps applied. Okay, I'm currently applying a 10 Hz sine wave to all 5 meters. This is at 100 Hz. You can see that in the upper right corner of the Hioki. This is with 10 kilohertz applied. You can see all the meters are reading this just fine. It's at 90 kilohertz and all the meters are working just fine. Unfortunately, this is the upper limit for the Hioki as well as the Fluke. You can see right at 100 kilohertz both meters roll over. It's with roughly 110 kilohertz applied. You can see right there it rolls over. Of course, these 2 meters are capable of reading into the megahertz. This is roughly the upper limit for the unit T. What we can do is select the frequency mode. And you can see both the unit T as well as the amp probe are capable of reading into the several megahertz. I'm currently applying a 1 Hz square wave at 50%. And all the meters are set to min-max, and we can see we're reading plus or minus 10 on the Brymen with an average of 0, and plus or minus 10 on the amp probe, and plus or minus 10 on the Fluke, and plus or minus 10 on the unit T, and plus or minus 10. So this is a 10.1, this is like 10.4 and 10.22. So this reads a little peaky with a square wave feeding into it. So what I've done is I've increased the frequency to 10 Hz and I'm giving it a 20% duty cycle. This is still plus or minus 10 volts. And we can see the Hioki now, the minimum is minus 7.7 and the maximum is 6.7. Our minimum on the Brymen is 6.06. and a maximum of 5.86. You can see on the amp probe it's a negative 3.3 for the max, and the minimum is minus 8.9, and our Fluke is reading minus 4.22 max and minus 7.82 min. Then we come over to our unit T and we can see minus 10.4 and plus 10.4. So this thing does a very good job capturing it. Unfortunately the number's wrong, but I think that that's probably because I need to do the compensation. If you remember, I applied the frequency response of this and it's not flat. It comes up and then dips back down. I think if I went through and trimmed this thing I could actually get a pretty accurate number out of this. It's just looking at the LCDs from different angles. It's your backlight kicking on. To me, all of them look pretty acceptable, but I think the coolest one is this one right here. is a pretty cool feature. I've got a small antenna. It's just connected up to an RF generator. I've gone ahead and swapped from about 2.4 gig down to about a megahertz. This looks like about the sweet spot right here. So about 5 millivolts of offset on the meter, which isn't too bad. This is at roughly 374 megahertz. Very few meters that I've looked at didn't have some type of susceptibility. Now the manual warns you about the thermocouple input, which isn't too surprising at all. This meter would actually do fairly well. I've seen meters that were much worse than this. Again, no effect in the diode or the capacitance ranges. It's really just the millivolts AC and DC. I went back and I looked at the meter, and these 4 transistors that they're using for the clamps are marked a VLR, and unfortunately I can't figure out what those parts actually are. It's possible they could be a 2SC5866. We know they're an NPN. I just suspect they're a small signal transistor. So what I've attempted to do is mock up the front end of this BM235. This is the test board that I've used in other videos. So on the front end we can see I've got a 1K resistor. That's followed by a small 5mm PTC that's 1.5K roughly. That goes into the same type of MOV that they're using. This is an 07D821. The larger 10mm MOV they're using is a 10D102K. And the part that I'm using is a ZNR V10102. These are both 1kV parts. And then what I've done is I've taken 2 small signal transistors, it's a 3904, and I place those back to back to act as our clamp. The problem that I see with this type of design is when the PTCs break over, this resistor here will limit the current going into the MOVs. However, the current going back into this clamp, there's no current limit for that. So basically I end up with about 2 kV at this node where this is going to clamp at, and I have a source impedance of roughly 2.5K ohms. So it's very possible that it could save these, but typically what I'll see with these small PTCs is they'll break over, and once that breaks over, now we have a 2 kV source with a 1K ohm, and I'm not sure if these transistors are going to handle that. Now if this is indeed a 2SC5866, these parts are rated for 2 amps, and they may indeed actually survive this. Typically what I see downstream is these transistors will short. Usually what I see on the better meters is even though these will fail, we won't typically take out the IC chip. There'll normally be enough source impedance like we see with this meter to save the IC chip. So let's just go ahead and try this with the transient generator and see if we can maybe figure out where these 3904s would fail at. It may give us an idea of where this thing is actually going to fail. You can see we have our scope. It's attached to 2 high voltage probes. This one is going to be looking right across the output clamp, while this one is looking at the input to the test circuit. And of course we have the transient generator attached. So what we can see is this initial transient is 500 volts per division, or roughly 1 kV. And again, that's a 100 microsecond full width half height. One thing I forgot to mention is the MOV that I'm using. You may notice it's probably about twice as thick as the one that's used in the Brymen. This is actually rated for quite a bit more energy than the one in the Brymen. Okay, this is with just the MOVs installed. And you can see our 2 traces are and you can see our input trace on top and the blue trace on the bottom is the output, or across the clamp. And you can see it's basically having no effect. Let's go ahead and install the clamp. And you can see what's happened is that has greatly attenuated the output. Of course, this is what the actual IC would see. So again, my concern is that we're going to actually damage these diodes. And that seems correct, and let's go the other way, and that looks fine as well. So at least at 1000 volts, the 3904s seem to hold up just fine. So what we'll do is go ahead and increase that a little bit. This is going to be for a 2000 volt, 100 microsecond full width half height. So again, we'll just have a look with the meter. And let's see if these were damaged this time. That one appears to be fine. And this one appears to be fine. So I now have the generator set for 4000 volts. Of course, you can see I don't like running this thing much over 4000 volts. So that one's fine. And again, this one is fine. So that was 4000 volts. Just do a dry fire. You can see this is 100 microseconds per division, and this is 1000 volts per division. So the peak is roughly at 5 kV and roughly 100 microsecond full width half height. Again, this is always with a 2 ohm source impedance. Let's just see what happens. And this one appears to be fine. And this one appears to be fine. Let's have a look at the other components. This will be across the input resistor. So roughly 1K. And this will be across the PTC, so roughly 2.5K. So those appear correct. Now keep in mind, I don't know what PTC they're actually using. All I know is this is about the same diameter and it's a 1.5K. I have no idea as far as the current that they're using for the trip. Again, this is a much larger resistor, flame-proof, surge type. I'm not sure what exactly they have in theirs. This MOV is identical. I have no idea what they're using for transistors. So again, this gives me some confidence that this is going to survive at least to the level that this generator will put out. So the first test we're going to run with our transient generator is the 220 volt line test. Again, the transient generator will supply a 220 volt full rectified signal into the meter. So again, the transient generator monitors the current going into the meter, and if it sees the current go above about 40 milliamps, it's going to shut that voltage off. And again, that's to prevent any additional damage to this meter. So I'll go ahead and I'll run the meter through all of its modes, and let's just see if there's any problems. And again, I never test the current inputs. So let me go ahead and I'll functional test this thing real quick. So the meter didn't have any problems at all with that test. It's good. Next up, we'll be doing our ESD testing, and again, I'm just using a small grill starter. Again, people had asked about the voltage levels off of this. I went through and characterized that, and that's available in one of my videos if you're interested. So again, we'll be applying 5 transients, both positive and negative. Okay, I'll go ahead and functional test it. Looks like the BM235 survived that test. If we look at the data that I've collected so far, the meters that have failed the 220 volt line test are the TPI Summit TPI 194.2, the Unity UT20B, and the Tech Power TP2844R. The meters that had failed the piezo grill starter test were the Unity UT61D, the Unity UT61E, the X-Tech EX430, the Vichy VC99, and the Unity 181A. So the little Brymen's already beat out quite a few. Next, we'll be applying a very limited surge test to the meter, and we'll see what level it actually fails at, or if it does at all. So we're all set up to run our first surge test. So again, this is 1000 volts per division. It's 100 microsecond full with half height. And again, I'll be applying 5 transients, both positive and negative with each mode of the meter. Alright, so the little BM235 passed that test just fine. Looking at the meters that failed that test, the BK2705B, the circuit test DMR6550, the UTL DM2, the Southwire 12070T, and the Innova 3320. So again, we're at 1000 volts per division, or roughly 1.5 divisions up, or 1.5 kV. And again, we'll be applying 5 transients, positive and negative. Again, this is always with a 2 ohm source impedance. Okay, the Brymen passed that test just fine. So let's see, the meters that I've tested, the ones that have failed at the 1.5 kV level, the Amprobe AM530, which is one of the meters that I used as a comparison against this, the TechPower TP40, the Fluke 87V, and the Victor VC921. So again, I have the scope set for 1000 volts per division, or 2000 volts. Okay, the Brymen is still alive, no problems at all. The meters that failed at 2 kV are the Klein Tools MM2000. It looks like that was the only one. So I've got the transient generator reprogrammed. Again, 1000 volts per division, or roughly 2,500 volts. And here we go. Alright, so the Brymen survived that test just fine. So again, that was 2,500 volts. Looks like there was only one meter that had failed at that level, and that was the Greenlee DM20. So you can see I've reprogrammed the generator for 3,000 volts. Alright, so the 235 passed that test just fine. I didn't have any meters that had actually failed at 3 kV. You can see roughly 4,000 volts peak now. And a little difficult to tell. I've got the cursor readouts and it looks like the maximum is 3.98 kV. Looks like we passed that test just fine. The only meter that had failed at that level was the Unity UT10A. And you can see I have the transient generator reprogrammed. Scope's reading roughly 5.07 kV peak. Go ahead and get started. Alright, we just lost power at our house, so I've reset the generator and we'll just continue our testing. Looks like the BM235 survived that test just fine. The meters that had failed at that level were the Hold Peak HP760H, the Unity 139C, and the Keysight 1231A. So this little Brymen has done better than my Keysight meter did. Of course, I wasn't able to repair the Keysight meter, but I'm hoping with this one, if we damage it, that we will be able to repair it. So this test will be with the generator turned all the way up. This is roughly about 5.8 kV peak. Alright, so the Brymen BM235 survived all the testing we could do with this generator. So what I've done is I've brought out the original generator and I've strapped this thing for 6,000 volts. So you can see this is roughly 1,000 volts per division. Scope is calculating 6 kV even right now, and the scope is still set for 100 microseconds per division. This has a full width half height of roughly 50 microseconds. Also, this generator has a 2 ohm source impedance. So again, this will be a 6 kV 50 microsecond full width half height 2 ohm source impedance. Okay, the little Brymen passed that test just fine. Looks like only one meter had failed that test, and that was the Unity UT15C. That was a high voltage probe that Unity makes. This is now set to 2 kV per division, and we can see we're roughly at 4 divisions up, or roughly 8,000 volts peak. Scope is measuring roughly 8.2 kV. So here we go. Okay, the Brymen had no trouble with that test. Again, that was 8,000 volts. Next, we're going to be running at 10,000 volts. Again, this is going to be a 50 microsecond full width half height, 2 ohm source impedance. Here we go. Okay, that's it. Alright, so the little Brymen survived that test. Again, that was a 10,000 volt, 50 microsecond full width half height, 2 ohm source impedance. So the other meters that failed at the same 10 kV test, we have the 17B Plus. This is the least robust of the Asian made flukes that I've tested. This damaged an op amp and I was able to repair the meter. It is 100% functional now. Another meter that had some problems at this level was the Hioki DT4252. Now this meter, I didn't actually damage anything electrically. What had happened is there's a little plastic spacer that runs up through a slit in the board, and it was actually arcing around that plastic, and the plastic was slowly degrading. So if we look at the meters that didn't have any trouble at this level, we have the Fluke 115, the Fluke 101, and while I didn't test it specifically on this generator, I ran the Fluke 115 all the way up to a 15,000 volt transient with a full width half height of 100 microsecond. And that's where that meter failed at. So what about the Brymen BM869S? Well, I didn't have this transient generator where I could set the different levels at that time. So I ran it at the last level that I had tested the 101 at. And that was 13,000 volts with a 2 ohm source impedance. And that damaged that meter. Again, I was able to go ahead and repair it. So if you're new to watching my videos, one of the things I should mention is I fully functional test the meter after each transient test. And I don't show that in the video just to save some time. I thought what I'd do is just run this through some basic tests. Here you can see my two Brymens are both attached to my fluke calibrator. And you can see I have a 10 volt signal applied. This is with the reference set to 1 volt. This is with our reference set to 1 millivolt. You can see the conductivity test works just fine. I had gone through my conductance test with this meter. It has an open circuit voltage of 1.7 volts. It has a short circuit current of 162 microamps. The resistance for a short was 152 ohms. And it reopens at 304 ohms. So, you know, fair amount of hysteresis there. The maximum 50% duty cycle waveform I could feed into this and have it trigger correctly was 5.6 hertz, and using a 2 hertz signal, the lowest pulse width that I could feed into it and have it detect a trigger was 18 milliseconds. This is with a 0.5 ohm resistor. This is with a 1 ohm resistor. This is a 50 ohm, 100 ohms, 1K, 10K, 100K, 1 meg, and 10 meg. Again, this is connecting to our thermocouple input. And in diode check, this is our short. And here's with a single diode, 2 diodes, 3 diodes. And this is with our 150 picofarad cap. This is 1 nanofarad, 0.1 microfarad, 1 microfarad, and 10 microfarads. So you can see that the testing that I've performed hasn't caused this meter to go out of calibration at all. So again, the BM235 costs about $130. That's on par with the Hioki DT4252 and the Fluke 115. The Brymen has some definite advantages over these two meters. It has a microamp range, non-contact voltage detection, a thermocouple input, and my favorite feature is it stores the settings like the large Brymen does. I've gotten real used to that with this meter, and I tell you, that's very difficult to go to another meter that's got a lot of functions and have it not store those settings. Of course, all three of these meters were certified by an outside party. If we look at the amp probe, again, this is about an $80 meter. Of course, this has a microamp range and can read temperature as well. It also has the non-contact voltage detection, but as you've seen, it's not near as sensitive as this Brymen meter. It's also a lower res meter, again 4000 count, and it's not as accurate. This meter also failed at 1.5 kV. When we look at the 61E, it does have a microamp range, but it doesn't have temperature. It also doesn't have a non-contact voltage detection, and it's not certified. The other thing I don't like about this meter, it doesn't even have a backlight. It's fairly accurate. It does have trim pots. I'm not sure how stable it is with temperature. Where these meters have all been certified to pass the EMC standards, these Unities, I'm not aware of any of them that have actually been certified to pass that. And it shows when I go to static test them. A couple of the shortcomings I see with the BM235, one of them is the low bandwidth. So in analog mode, this thing starts to roll off fairly quickly. The Hioki and the amp probe aren't a whole lot better, and I know for me personally that really wouldn't be much of a problem. I do some work where I need the higher frequency off a meter, but it's pretty rare. Normally I'll just grab a scope. The other thing that amazes me is that it doesn't really have a frequency counter. It can read the frequency when it's in the AC mode, but it might be nice having that dedicated input if you're wanting to read higher frequencies. A couple of the features that I like on this larger Brymen as well, the fact that it has 2 thermocouple inputs and that it can calculate the difference between the two. It also has this AC plus DC mode that I find very helpful. It can also display the 4 to 20 in a percentage. Not to mention it has the split display up here. It can also read a much shorter pulse than what this meter can. Obviously higher resolution is always nice, and it's a more accurate meter. But again, this meter costs not quite 2 times as much, but $100 more than what this one does. So you're going to expect, coming from the same manufacturer, this is obviously going to be a more capable meter. You know, and to be honest, when I got this meter, I wasn't sure how I was going to like it, but I'd like it. It's kind of like the little brother of this thing. You know, it's nice and small, so I could actually see taking this thing outside. It's very rugged, and it's got some very nice features that you don't see in meters that are priced that range, at least not in higher end meters. Of course, again, you could go with something like this amp probe, but this meter is not near as robust as these. I don't know if it was by luck or not, but I think Dave picked a very good meter in this one. I think Brymen did their job with it. It's definitely a very robust unit. It ranks right up there with the Flukes that I've tested. I don't see too many meters that'll run up as high as what we ran this meter. Maybe one day if I accumulate enough of them, we'll have a runoff between these Flukes and maybe this Brymen. Of course, this is not going to replace my favorite meter, which is this BM869S. You know, okay, yeah, it's smaller, but this has a lot more functionality. I've actually grown to really like this meter. I have yet to see another meter that I like as much as this one. So I'd like to remind you that I'm not paid to do any of these reviews. This isn't something that Dave or Brymen had contacted me about doing. I bought this meter out of pocket through normal channels. Well, I think that's going to be it for this video. I'd like to welcome all you new members. If you're interested in seeing reviews where we don't just talk about how well the meters are built and we actually put them into practice, this is definitely the channel to watch. You can see I have no qualms about running these meters up to failure. Well, until the next meter. Later.